So welcome to the debrief for the Web Scraping and APIs project. Hopefully you had a pretty good time with this. There were not really too many twists and turns. Sometimes I like to push you a little bit. Since we're in the data science content, try not to push you as much, especially because the next projects, when we start getting into the machine learning and natural language processing content, are going to be a little bit more of a push. So this time, I hope you found this relatively straightforward, where we're basically just taking the API calls that we've already talked about and we've already explored in the lecture material and just pushed a little bit of a step forward. So let's just go ahead and dive into it. So in this one, we have our normal process, which we, of course, follow pretty much every time. I'm actually going to skip, however, the RStudio API code because there are no files involved in doing this kind of work. Since we're pulling things from the internet and our data set comes from the internet, we don't really need it. Instead, we just have our libraries and our data importing, cleaning, analysis, and visualization section. So we're going to go ahead and start up a new script and get those sections set up. Our next goal is to just simply accomplish our first project, and our first part, I should say. This is in week 11-twitter.r. Goal 1 is to download per post like data for the most recent 1,000 posts from our stats. So that's going to involve a couple of pieces. One, we're going to need to get the Twitter library, of course. Step 2, we are going to need to actually log into our system. So I'm actually going to go ahead and copy paste all of my various access keys and such in here, just because otherwise it's going to take a little too much time, as well as the OAuth command. So as a reminder, once you need to get in, you're going to need to get those 4 pieces of information from your Twitter account on developer.twitter.com and logging into your application, your app. If you are going to use this, the reason that there are 2 sets, that the API versus the access, is because they're used for different purposes, and you can also give certain keys, read, write, or just read access. An important point here is because, as you notice, I have to write this in plain text in this file. If you're going to do, for example, put this on a web app and put Twitter access in a web app, a Shiny app on shinyapps.io, then that means that your login credentials will be available in plain text to anybody that can access that behind the scenes. So as a security approach, a security precaution, you would create an access key that only has read access and not write access to use in an app like that, unless you really, really needed write access for some reason. But for data collection, you probably wouldn't. So just be very cautious, be very cognizant of security issues and access issues and that kind of thing. So next we need to actually download per post like data from the most recent 1,000. So that's relatively simple. We're going to do our tweets, our search Twitter in our stats, and we're going to grab 1,000 of them. So as I mentioned in the lecture material, there are per post or per query limits in terms of how much data that you can get from Twitter. So again, an advantage to Twitter is that it automatically parses out how many individual requests would be necessary in order to send 1,000, in order to collect 1,000 cases worth of data, and then it actually only sends that number, the number that you actually need. So that's very convenient. We have now a list of 1,000 items, so that looks right. We need to strip it down. Do we actually want to have clean data? Oh, I see a do not include retweets down a little bit later, so we do. So let's do tweets clean is strip retweets tweets. It'll only take a second. And then we're going to go ahead and convert that into a data frame using the there it is, list to df. It's just such a terrible capitalization scheme of tweets CL. And now we have a data frame containing 205. In this case, your number might be slightly different because you'll be doing this at a different time than I will. But 1/5 real information and 80% echo chamber sounds about right for Twitter. So we move to, actually might even be a little high. We move to the next stage. Create a tibble called tweets_tibble. Okay, tweets tibble. Containing two columns, screen name of the person tweeting, more than two, I guess, it's really 4. The screen name of the person tweeting, the content of their tweet, how many times they've been liked, favorite, and how many times they've been retweeted. So we will collect all of that. Actually, we already have all of that in our data frame, don't we? So I'm just going to take a look at it. Yeah, yep, I see all of that. There's our favorite count and our text. So let's just use a tidyverse function, select. We're going to select tweets tibble, and from tweets tibble, we're going to let's get the full name, screen name, which is screen name, and the content of the tweet, which is in text. Then 3 is number of times liked, favorited, so that's favorite count, and how many times they've been retweeted, so that's retweet count, there we go. And of course, we could look in the documentation for, it's not already called tweets tibble, it's called tweets data frame. So we could look in the documentation in Twitter's developer documentation to figure out what all of those actually mean. I think it's pretty obvious in this case, but if you weren't sure and you looked at, for example, say you didn't exactly understand where that ID number was used and what it was for, I'll tell you now it's actually an identifier for the message itself, but you wouldn't know that unless you'd read the documentation. In which case you'd want to look at the developer docs and go look it up if you needed to use identifiers for whatever reason. All right, so we've now subsetted, do not include retweets. We did that, great. Is there a relationship between length of tweet and retweet popularity? And what about length of tweet and likes, favorites? So length of tweet is a new piece of information that we don't have, but it capitalizes on a skill set we had before. I'm gonna go ahead and add a pipe to my selection account, or my select statement. Add a mutate, and we're going to call this tweet length, and we're going to use the stringer package, which is part of tidyverse, and the str length function. And that we might as well go take a look at it, make sure it looks right. Yep, add a column where every number is different and captures the length. We can also go ahead and sort that just so that we can get a rough visual estimation, make sure it looks right. Yep, so we see the lengths gradually increasing, up and up and up. So looks like that worked. So hopefully you remembered that this came in the stringer function and it's something we already have done. There's also a len command, I think, which probably would have worked just as well. I like trying to stay in tidyverse where we can. It also is a little more predictable in terms of what happens when you do these tests. So actually, let's also go ahead and make sure that's the right data type. Integer, good. And favorite count and retweet count are numeric, so good enough. Integer or numeric would work for them. So that means if we want to next figure out the relationships between those variables, we need to run an appropriate analysis. So it's really up to you at this point as to what you did. I'm going to just show you a correlation for the sake of simplicity and because we've already covered it. You might, however, want to look in other types of regressions for reasons that we will get into in just a moment, especially when we look at the visualization. So I'm going to do a correlation test with tweets tibble, tweetlen, and we're going to compare that to tweets tibble, what was the first one, favorite count. See what we got. Correlation of 0.097, a p-value of 0.16, so not statistically significant and also pretty small. Tweets tibble, tweetlen, and tweets tibble retweet count. And this one is correlation 0.169, p-value 0.015, so that one is statistically significant. Here is a fun fact for you. If you are the type that is typically relied on statistical significance, I could just continuously increase the sample size here effectively forever. So there's no real reason we chose 1,000. That was just for the sake of example. I could have easily have chosen 5,000 or 10,000 or 100,000. And when you get up in the 100,000s, then the statistically significant correlation goes down to like 0.02-ish. So you can very easily find relationships that are statistically significant that are not practically significant. So the important piece here would still be to look at these correlations for practical significance. And you can see there's a correlation of 0.169. That's really already only 2.8% of the variance in one explained by another. Is that meaningful? I don't know. If you were doing the research, and actually this was an interesting question, then you might have an opinion on that. But it is a thing to think about anytime you do this kind of scraping projects, because you can always get a bigger sample. Not always, but almost always get a bigger sample. On social media, you can virtually... I don't want to say always because I'm an academic, but I would say almost always get a larger sample when using social media data until the point where you actually have a population of social media for whatever context of interest that you're looking at. So be cautious in that. We talk about that issue a little bit in the paper I referenced during the lecture, and just be careful. So we have statistical tests. Create visualizations of each of these. I'm also moving these in the wrong place. There's our analyses, and our visualizations doesn't say what to do, so we'll just go ahead and do a generic ggplot using tweets tibble with an aesthetic of our x variable is going to be tweet length probably, because there's really kind of an implicit question here of if you write longer tweets, do people like it more? We didn't investigate it causally, so that's kind of fake out, but probably makes more sense to look at it this way rather than any other, at least. Geom smooth. Did we need to use any particular format? Nope. So I'm just going to use Geom smooth, which is going to default to a low S smooth, and Geom point, so we get the raw data. We'll see what we end up with. Ooh, yeah, you can see it looks it's a little curvy, because we have a lot of outlying cases in a lot of weird places. And you can also see a lot of zeros on favorite count. Tweet length seems to be more, if not normal, at least negatively skewed normal distribution, whereas favorite count, that's a lot harder to say. I would probably put that at Poisson distribution or maybe something else. So if we were really doing this, we would want to choose a more appropriate analytic strategy for skewed data. Maybe we do transformations. Maybe we'd use more robust analytic statistics. I don't know. Maybe even look at non-parametrics and could have just run a Spearman's or whatever else. So think carefully and make sure you run all your diagnostics when you do this kind of work. But for now, we're just showing that we can do this. So there's no real, it's not called retweet count. Oh, no, it is. Retweet count. Where there's not really any specific goal here in terms of visualization or in terms of hypothesis testing, so we're just doing this for the sake of example. That's a real weird curve off at the end. We can probably, and remember, we could also see that specific regression line implied by the correlation if we put a method equals LM in there. And see there, you can see your slight positive correlation. But man, that's skewed. There's a lot of influential cases in there. I don't know if I trust that, but that's the kind of thing you would want to think about if you were doing this for realsies. So there you go. So we have our first file. That's it. Completely done. Other things that you might have done differently in here. Again, you might have taken this and used our, the length functions that are part of base R rather than doing this in the dplyr fashion. You might have subsetted specific columns instead of using select within dplyr, although I prefer that. You might have done different analyses here instead of correlations, which is perfectly fine. And for your plots, if you did alternative statistics, then you might have found that different visualizations made more sense. Another thing, if you were really feeling clever about it, that you could have recombined the entire data set into one very long, you could have restructured it into one long data set, and then use that to create two lines side by side, so you could actually see the regression lines, and perhaps in different colors, from the favorites and the retweets as two separate lines. Although you need different axes because the scales are different. So any of those differences would be totally fine, totally up to you if those are the kind of thing that you find interesting. We next move to the second one. So I'm going to go ahead, just because I'm very lazy and don't like typing, I'm going to go ahead and set us up like this. And we'll go ahead and look at the next project. So this one would be in week 11-scholar.r. There is no Google Scholar API. That's a thing people have complained about a lot. People really want there to be a Google Scholar API. I think the reason Google doesn't do it is because there's literally financially no reason to, because it would only be taken advantage of by scholars, and scholars don't tend to spend a lot of money. Google Scholar, the existence of Google Scholar has actually been called into question a few times. It's so popular at this point, I think there would be a bit of a revolt if it got removed. But at the same time, probably not wise to think of it as a permanent resource. Regardless of that, I think it's an interesting exercise to try to use it as a source of information for web scraping. So that is what we're going to do. So first I'm going to go ahead and load the tidyverse, because I always load the tidyverse. I actually realized in the last file we didn't load the tidyverse. Must have already had it loaded. Whoops. I'm going to go ahead and load tidyverse, and I'm also going to load rvest, because that's where our HTML processing is going to occur. So that gets us ready for data capture. It says choose someone's Google Scholar page. Ooh. Does not matter who you choose as long as they have at least 10 papers. Using our code alone, read this page and create a single tibble called profile_tibble, containing columns representing name of article, author list, year, and citation count. A person with 20 papers listed should have 80 pieces of data. So that is an interesting set of issues. So on the bottom we have, don't worry about anything past the first 20 citations. So that's good. So if you go to Google Scholar, you will see that there's a button at the bottom called Show More, right? And if you hit Show More, it will add, almost out of thin air, an additional up to 20. Actually, it added significantly more articles just based on pushing that button. So the question becomes, how does it do that? Because if you throw this into your garden variety web scraping software, as you probably did, you might have noticed that you only get 20 back. So what exactly is that button, and what does that button mean? Well, that button is essentially a JavaScript call. So by default, it's only going to show you the first 20 cases, because the first 20 cases are easy to get. And for the average person looking up someone on Google Scholar, they're not actually concerned with an exhaustive look at all their citations. They just want to say, all right, what's the most popular stuff this person has done? Done, and you're finished. So through their internal research, they've realized that they can save on a lot of database calls if they just automatically limit that first request to 20. So if you don't want to do that, that means you can push the button. And what happens when you push the button is it invokes JavaScript to download in real time additional citations and display them. So that's a problem for web scraping. If you're using a more modern web scraping framework, such as the one like a Scrapey within the Python system, or a Beautiful Soup even, there are ways to get around this problem. What you essentially do is you simulate an actual real web browser. It'll run in another window, and you say, okay, web browser, first go to this web page, then click on this part of the screen, then click on this button over here. And those instructions can be used to actually generate and record that kind of dynamically produced data on the fly. If you're just using R, which is just kind of passively downloading the starter web page, whatever it might be, and then allowing you to process it, then you don't have that kind of control. So you're not going to be able to do that kind of thing. So that's why the instructions here only ask for 20. And if you really wanted more than that, you would need to use something other than rvest and R, which just frankly are not capable of the kind of deep level manipulation of like a web browser in another window that Python would be, for example. So this is why you tend to see most quote unquote serious data science applications start to move into the Python space, because Python is such a general purpose programming language. You can use it for almost anything. That means that if you need to dip out of the statistical space and move more into the file management or web browsing or whatever it is space, those tools are already available to you and you don't have to switch between languages. So that's just a thought. For here, we're just going to download the first 20 very straightforwardly. And I could download myself, but I think what I'm going to do is actually I'm going to download citations from my favorite author, probably your favorite author too, if you don't realize it. And that is the famed et al. Et al. Is the most published author in all of academia. You can see here an H-index at all time of 333 with 2.9 million citations. So just a very popular author. Et al. Is, as noted in et al.'s profile, an academic superstar. So we're going to go ahead and grab the information that we want from et al.'s profile. So that means the number one step is we're going to create a variable to record this one file, and it's going to be based on that file right there. So now we have an HTML object stored inside scholar_HTML, and it's actually an XML object technically because XML is or HTML is a type of XML. But now we need to grab specific pieces of information. So that means we first need to capture the nodes, which is like the location in the file, using the HTML nodes command. And we're gonna have to do that once for each individual type of data. And we're gonna also have to use selector gadget in order to pull each of them. All right, so what do we need? We need first name of article. So we go into selector gadget, we choose the names of the articles, no gratuitous yellow, nope. And we'll click and we'll copy and we'll go back into our studio and we'll use that as our selector. Run, and then Scholar nodes text maybe? No, not Scholar nodes text. Scholar text, gotta remember your own naming conventions. Name, HTML text, Scholar nodes name. There we go, that should work, right? And if we look over here at Scholar's, oh boy, Scholar text name, can't type, Scholar text name, then we get, there it is, yeah, the full list of 20, and we can cross-reference that protein measurement with the folin-phenol reagent, and phenol, oh boy, folin-phenol reagent, all of that is still there. So it looks like, at least on the surface, we have successfully grabbed that first set. We're now gonna repeat this process, several more times, 3 more in fact, in order to grab, what are we grabbing? Author list, year, and citation count. So let's do authors, year, and cites. Okay, and that's there, and that's there. So next we need to figure out how to change all of these. So next was authors. So let me enable selector gadget. Let's choose some authors. Oh, we're grabbing some extra info there we don't want. I think, yep, that looks like that's it. So we'll take this as our CSS selector, run, then look at Scholar text authors. Yep, looks like that worked just fine. You can see our et al.'s right there. Then we clear this out, and next one was year, I think. Oh, got some extra. That's down to what we want. Copy, back into our studio, paste, run, then double check, Scholar text year. Looks good. And finally, clear, citations, deselect, select, copy, paste, run, Scholar text cites. And those look like the numbers that we were just looking at. 209,000 citations on one article. That is, I don't know what that is. So we got all the data that we need, but now they're all in different places. They're not all in one location. So that means we need to put everything together. And what was it supposed to be called? Profile_Tibble. So we're gonna do profile_Tibble gets Tibble, and we're going to put in Scholar text name, Scholar text authors, Scholar text year, and Scholar text cites. Hopefully that'll work. And if so, we should be able to open profile, and there we go. So in about less than 10 minutes, we've managed to recreate this one web page and pull all those data down. 100% reliability in terms of exactly representing what that web page contains. So good job for us. We move into next phase, which is going to be doing a thing. Calculate a correlation between year and citation count. Well, that's actually going to be a little bit difficult. So let's go ahead and try it naively, just so you can see what. And you might have run into this problem yourself. If we did profile, Tibble, Scholar, text, and really the problem is right there in the name. must be numeric. So these are text, so these are not numeric, even though we know them as numeric. If we go over and look at the list over here, you can see that they're stored as character vectors, but we need to change them into numeric vectors. So I'm going to actually go back up to my table and give myself some better names. Name, authors, year, and cites. And I'm going to do an as numeric on each of those to coerce it back to the format that I want it to be. If we look back over here, yep, we're up to numeric now, and I'm going to change this back to year and this to cites because we just changed them. And run the correlation. There it is, negative 0.42, which is fully consistent with prior theory on bibliometric patterns in that the longer something has been cited, or the longer something has been published, the more likely it is to have citations. So success. We have calculated correlation. Do we need anything else? Nope. That's it, just a correlation. And then in visualization, create a scatter plot showing this regression superimposing a regression line. So this time we're not just doing whatever the heck format we want to. And I'm actually going to copy my ggplot just again because I hate having to retype things. Except this time we're going to do profile tibble, and on the x-axis we want year and cites. We'll just run it. That's a weird shape, so we've got a few outliers there. We're going to add our method lm to make it a regression line, and there we go. So the further forward in time it is, the fewer cites it is likely to have. You might even use this, and this is actually kind of an interesting exercise anyway, because you could even use this to say, wow, some of these outlying cases, which are way out there, maybe that means these were particularly influential in the career of et al. Perhaps et al. Really made a difference in those particular pieces. Anyway, that is it for scraping in APIs. What I hope that you pull out of this is that the base skills for just grabbing the data, not that complicated. It's really about understanding where the data are represented and figuring out, well, how do I just poke at this in such a way that I can grab what I want? And beyond that, what kind of patterns do I need to use in order to grab the full sets of everything I want? Say, for example, we were interested in grabbing profiles from 10 different people. We would take this entire set of HTML coding, where we're converting the HTML documents back into data sets. We would wrap that inside a function, and then we would call that function 20 times for 20 different authors, and we would just add one row at a time to kind of a master data set that we would build piece by piece. If we wanted to be really fancy about it, we might also add in some error handling. So in case somebody was missing or a website was wrong, that it would record that error in a log file so we could go back and fix it later. This is the exact kind of thing that people do in modern day data journalism and also do in modern social scientific projects involving data collection, because you want to be absolutely sure that every case is represented authentically in your data set that was in the original website. So you engage in a lot of behaviors that are central to ensuring that your data set is accurate. And so that involves really going back and testing, going back and checking. You saw how it several times just instinctively here, I went back to the original data set and been like, oh, is that what the numbers, do they match up? Yeah, okay, we're good. That kind of process should be baked in as soon as possible to make sure you always end up with the most accurate data that you can. But yeah, otherwise that is all for our APIs and web scraping.